10,
VLS go for main engine start.
6, 5, 4, 3, 2, 1. And booster ignition liftoff of Space Shuttle Discovery, taking the space station to full power for full science.
Every civilization, from the first humans who gazed up at the night sky to the modern physicists peering through their telescopes, has asked the same question: how far can we go? So before you get comfortable, take a moment to like the video and subscribe. But only if you genuinely enjoy what I do here and tell me in the comments where you are and what time it is right now. I always find it fascinating to see our little community scattered across the globe. Now, dim the lights, maybe turn on a fan for that soft background hum. And let's ease into tonight's journey together. It is the question that humbles, terrifies, and inspires. The moon was once unthinkable. Mars was once unreachable. The stars were once the realm of gods, myths, and monsters. But light, the very thing that carries the sun's warmth to our eyes, has always taunted humanity with its perfect constancy, a cosmic speed limit written into the fabric of reality itself. And yet, we dream. We dream because distance has never stopped us before. Oceans fell, continents were crossed, skies were conquered. Every generation inherits the belief that the next horizon will finally be the one without limits. Space feels like that horizon, vast, silent, infinite. A final frontier waiting patiently for our arrival. But the universe does not care about our dreams. The uncomfortable truth, the one buried beneath documentaries, headlines, and glossy renderings of future colonies, is that right now, humanity can barely leave its home planet at all. Our reach into space is not a sweeping arc across the cosmos. It is a thin, fragile thread extending just beyond Earth's atmosphere, trembling under the strain of physics, biology, and time. The distance between what we imagine and what we can actually do has never been wider. To understand how far we can travel through space right now, we must first confront the illusion that space is open to us. Because space does not begin with freedom, it begins with confinement. From the ground, the sky looks like an invitation, blue fading into black, clouds dissolving into stars. There are no visible barriers, no signs that say, stop. It feels as though all that separates us from the universe is courage and technology. Build the rocket, light the engines, go. But the sky lies. The moment you leave Earth, you encounter the first and most brutal reality of space travel. Everything that keeps you alive disappears at once. Air, pressure, temperature stability, protection from radiation, gravity. Every condition that shaped human biology over millions of years vanishes within minutes. Space is not an environment humans enter, it is an environment humans must fight. This is why the question, how far can we go, is never really about distance. It is about survivability. How long can fragile systems continue to function when nothing outside them helps at all? How long can the human body endure conditions it was never designed to face? Distance in space is not measured in kilometers. It is measured in time without failure. And failure is inevitable. The first great illusion humanity carries into space is scale. When we look up, everything appears close. The moon looks like a reachable object. Mars glows like a neighbor. Stars seem scattered just beyond them, as if they belong to the same neighborhood. Our eyes compress unimaginable distances into a flat dome of light. But the universe is not scaled for human intuition. The moon is nearly 400,000 kilometers away. That distance represents the farthest humans have ever physically traveled, a record set over half a century ago and never broken since. Mars, often described casually as the next step, is not twice as far or 10 times as far, but sometimes 500 times farther, depending on orbital positions. And beyond Mars, the distances explode into numbers so large they lose meaning. Jupiter is hundreds of millions of kilometers away. Saturn is over 1 billion. The nearest star system, Proxima Centauri, lies more than 4 light-years away. a distance that would take tens of thousands of years to cross using our fastest spacecraft. And that is just the local neighborhood. Yet we speak as though these places are simply waiting for us. This illusion persists because human history has trained us to believe that distance always yields to progress. There was a time when crossing an ocean took months and killed thousands. Now it takes hours. There was a time when flight itself was impossible. Now it is routine. Every past barrier fell eventually, so surely space will fall too. But space is not a continuation of Earth's challenges. It is a different category of problem. On Earth, distance is solved with infrastructure. Roads, fuel stations, cities, farms, hospitals, redundancy. When something breaks, help can arrive. When supplies run low, more can be delivered. When humans weaken, environments support recovery. In space, there is no infrastructure. There is no help. There is no recovery. Every mission carries everything it will ever need from the moment it leaves Earth. Oxygen must be recycled. Water must be purified endlessly. Food must last. Power must continue flowing. Heat must be regulated perfectly. Radiation must be blocked or endured. And every one of these systems must work without interruption, sometimes for years. A single failure, one cracked seal, one micrometeorite impact, one software glitch, can end everything. This is why space travel has not followed the same exponential curve as computing or communications. Physics does not compound like software. The energy required to lift mass off Earth has not changed since the first rocket equation was written. The limits imposed by chemical propulsion remain stubbornly fixed. You can optimize engines, reduce weight, improve materials, but you cannot escape the fundamental cost. Leaving Earth is violently expensive. It requires reaching orbital velocity, nearly 28,000 kilometers per hour, just to avoid falling back down. That speed is not optional. It is the price of admission. Miss it, and gravity reclaims you instantly. Reach it, and you are still not free. You are merely falling around Earth instead of into it. This is the narrow ledge humanity occupies today. Low Earth orbit, where satellites and the International Space Station reside, is not deep space. It is still wrapped in Earth's magnetic field, still close enough for rescue, still within hours of home. Astronauts aboard the ISS are closer to Earth than many cities are to each other by road, and even there, the human body begins to fail. Bones lose density, muscles weaken, fluids shift toward the head, vision deteriorates, immune systems falter, radiation slowly damages DNA. The longer humans remain in orbit, the clearer the message becomes. Space erodes life. This is not a design flaw in spacecraft. It is a mismatch between biology and reality. Which brings us to another illusion, perhaps the most dangerous one, that robotic success equals human capability. We have sent machines to the edges of the solar system. Voyager has crossed into interstellar space. New Horizons has flown past Pluto. Probes orbit distant planets and land on alien worlds. These achievements are extraordinary, but they do not mean humans can follow. Machines do not breathe. Machines do not age. Machines do not suffer isolation. Machines do not care if the journey takes decades. A robotic probe can drift for 50 years and still complete its mission. A human cannot. Human space travel is constrained not just by engineering, but by biology and psychology. A crewed mission must protect fragile bodies from radiation that would slowly kill them. It must prevent muscle and bone loss severe enough to make walking impossible upon arrival. It must maintain mental health in confined spaces, with no escape, no privacy, and no rescue. And it must do all of this while remaining perfectly reliable for years. Right now, we cannot. This is why, despite all the promises, all the plans, and all the ambition, humans have not traveled beyond the moon since 1972. Not because we forgot how, not because we lack courage, but because the risks are enormous, the costs are staggering, and the margin for error is zero. The Apollo missions were not proof that deep space travel is routine. They were proof that it is extraordinarily dangerous. Engineers knew astronauts could die. Politicians accepted the risk because the symbolic reward outweighed the human cost. That calculus no longer exists. Modern society does not tolerate loss the same way. Today, astronauts are not expendable heroes in a race for dominance. They are highly trained professionals whose deaths would halt programs, shatter public support, and end careers. This is not cowardice. It is realism. Space demands sacrifices. Modern civilization is no longer willing to make. And then there is time. The silent enemy that undermines every dream of distant travel. Even at incredible speeds, space journeys take months, years, or lifetimes. Hardware degrades, electronics fail, fuel boils off, political priorities change, budgets vanish. Missions that last decades must survive not just physics, but governments, economies, and public interest. Interstellar travel is not blocked by imagination. It is blocked by durability. This is why most visions of humanity spreading through the galaxy quietly ignore the present. They leap over centuries of unsolved problems and land in a future where everything works because the story requires it to. But reality does not bend to narrative convenience. Right now, humanity is a species tightly bound to a single world. We rely on Earth's atmosphere to breathe, its magnetic field to shield us, its gravity to maintain our bodies, and its ecosystems to sustain us in ways we barely understand. Remove those supports, and survival becomes temporary, artificial, and fragile. This is the truth hiding behind the question, how far can we go? At this moment in history, our answer is humbling. We can reach low Earth orbit with reliability. We can reach the moon with enormous effort. We can send machines across the solar system slowly. And that is all. Everything beyond that, Mars colonies, asteroid mining empires, human voyages to the stars, exists in concept art and confidence, not capability. They are dreams projected far into the future, assuming that physics, biology, and time will eventually step aside. History warns us against that assumption. Every age believes it stands on the edge of transcendence. Every age underestimates the stubbornness of limits. And every age eventually learns that progress is not a straight line. It is a negotiation with reality. Space is not waiting for us. It is not impressed by our technology. It is not moved by our ambition. It is vast, indifferent, and lethal. The illusion of unlimited space is comforting because it suggests escape from Earth's problems, from scarcity, from consequence. It whispers that no matter what happens here, there is always somewhere else to go. But right now, that escape does not exist. Right now, Earth is not just our home, it is our lifeline. And until we confront that honestly, without hype, without fantasy, without denial, we will continue to misunderstand how far we can really travel. Because before we talk about Mars, before we talk about asteroids, before we talk about the stars, we must face the first and most unforgiving truth of space travel. Leaving Earth is the hardest journey humanity has ever attempted, and we are still at the very beginning. Every journey into space begins with the same lie. It tells us that once we leave the ground, the hard part is over. That once the engines roar and the rocket rises, humanity has broken free. That the sky is behind us and the universe is ahead. But in reality, the moment a spacecraft leaves Earth is when the real struggle begins. Because Earth is not merely a starting point, it is a gravity well, deep, relentless, and unforgiving. A planet that has spent billions of years perfecting the art of holding on to everything it touches. Oceans, atmosphere, life, and us. Earth does not let go easily. To understand how far we can travel through space right now, we must confront the first and most absolute barrier to exploration. Getting off the planet at all, not symbolically, not briefly, but in a way that is repeatable, sustainable, and survivable. This is the wall humanity still crashes into every time it dreams too far ahead. From the surface, Earth feels gentle. Gravity is invisible, constant, so familiar that we forget it exists. We walk, run, build, and fly without ever thinking about the force pinning every molecule of our bodies to the ground. But gravity is not weak, it is simply patient. To escape Earth's grip, a spacecraft must reach a specific speed, orbital velocity, roughly 7.8 kilometers per second, nearly 28,000 kilometers per hour. Anything slower and gravity wins. Anything faster and you still are not free. You are merely falling endlessly around the planet instead of into it. This is what orbit really is, perpetual falling that never reaches the ground. And reaching that state requires energy on a scale that dominates everything else about space travel. Most people assume rockets are about height. They imagine spacecraft climbing upward, breaking through layers of atmosphere, and emerging into space like submarines surfacing from water. But height is almost irrelevant. You could go straight up 1,000 kilometers and still fall back to Earth. What matters is speed, and speed is expensive. To achieve orbital velocity, rockets must burn unimaginable amounts of fuel in a matter of minutes. The majority of a launch vehicle's mass is not crew, cargo, or science equipment. It is fuel. Fuel whose only purpose is to lift more fuel. This is not inefficiency, it is physics. The rocket equation is brutal in its simplicity. Every additional kilogram you want in orbit requires exponentially more fuel at launch. Add life support systems, radiation shielding, structural reinforcement, redundancy, and the fuel requirement balloons beyond reason. This is why rockets look the way they do, towering stacks of propellant wrapped around a tiny payload. Humanity does not ride rockets into space. We cling to controlled explosions and hope they last long enough, and they often don't. Rocket launches remain among the most dangerous activities humans perform. Despite decades of progress, every launch balances on the edge of catastrophe. Engines must ignite perfectly. Combustion must remain stable. Guidance systems must function flawlessly. Structural loads must hold under forces that would tear ordinary machines apart. When something goes wrong, there is no recovery. There is only debris. This is why access to orbit remains rare, expensive, and fragile. A single launch failure can ground entire programs for years. A single accident can end political support overnight. The physics does not care how advanced we become. The margin for error remains thin. And yet, orbit is still not freedom. Low Earth orbit, where satellites and space stations reside, is often described as being in space. Technically, that is true. Practically, it is misleading. Astronauts in orbit are still deeply bound to Earth. They circle it every 90 minutes. They rely on Earth-based infrastructure for communication, navigation, resupply, and rescue. Orbit is not a destination. It is a knife-edge balance. The International Space Station is a perfect example. It is one of the most complex machines ever built, assembled piece by piece over decades at staggering cost. It orbits just 400 kilometers above Earth, closer than many commercial flights travel horizontally. And even at that distance, sustaining human life is an ongoing struggle. Astronauts aboard the ISS live inside a sealed environment that must regulate air composition, remove carbon dioxide, recycle water, manage waste, control temperature, and shield against radiation. Every system is redundant. Every component is monitored constantly. Failure is not an option. And still, problems occur. Leaks, electrical faults, cooling failures, fire hazards, ammonia system malfunctions, micrometeoroid impacts. Each incident is a reminder that space is not a place where humans belong naturally. Survival depends entirely on machinery working without pause. And even when everything works, the human body pays a price. In microgravity, bones lose density because they are no longer bearing weight. Muscles atrophy because they are no longer resisting gravity. the cardiovascular system changes. Fluids shift upward, increasing pressure in the skull and damaging eyesight. The immune system weakens. Radiation exposure accumulates silently, increasing cancer risk. These effects begin within days. They worsen over months, and they do not fully reverse upon return. Orbit, the closest thing we have to living in space, actively degrades human health. This matters because every destination beyond orbit is farther, longer, and harsher. Before humanity can think seriously about traveling to the moon regularly, let alone Mars, it must first master long-duration survival in orbit. And that mastery remains incomplete. The ISS exists because of constant resupply from Earth: food, water, oxygen, spare parts, all delivered by rockets that must succeed every time. Remove Earth from the equation, and the system collapses. This is the first wall: dependence. Every crewed mission today is tethered to Earth by logistics. Even missions that travel beyond orbit, such as the Apollo missions, were brief, tightly constrained, and extraordinarily risky. Astronauts went to the moon for days, not months. They carried everything they needed. There was no backup. Apollo succeeded not because the problem was solved, but because the risk was accepted. That acceptance no longer exists. Modern spaceflight is constrained by ethics, law, and public tolerance. Astronauts are not test subjects. Their lives cannot be gambled casually. Every mission must justify its risk against its benefit. Every failure invites scrutiny, investigation, and cancellation. This is why human exploration has stalled at orbit for decades. It is not a failure of ambition. It is a collision with reality. Earth-to-orbit travel also imposes a hidden cost that compounds every other challenge. Mass limits. Every kilogram sent into orbit costs tens of thousands of dollars. Even with reusable rockets, the economics remain unforgiving. This forces brutal trade-offs. Shielding is reduced to save weight. Redundancy is minimized. Comfort is sacrificed. Safety margins are trimmed. These compromises accumulate. A spacecraft designed for orbit cannot simply be scaled up for deep space. Longer missions require more supplies, more protection, more redundancy, all of which demand more mass. More mass demands more fuel. More fuel demands larger rockets. Larger rockets increase risk and cost. This is the tyranny of the rocket equation playing out at civilization scale. And this is why concepts like Mars colonization remain trapped on paper. The challenge is not reaching Mars once. It is reaching Mars reliably, repeatedly, and without killing the people who go. Every extra day in transit multiplies exposure to radiation. Outside Earth's magnetic field, astronauts are bombarded by cosmic rays and solar particles that damage cells and increase cancer risk. Shielding against this radiation requires mass that is expensive to launch and difficult to accelerate. This is why most serious Mars mission studies quietly accept that crews will absorb radiation doses close to or exceeding current safety limits. The technology to fully protect humans does not yet exist in a practical form. Orbit protects us. Deep space does not. Which brings us back to the central truth of this section. Getting to orbit is not the end of Earth's grip. It is proof of it. Even in orbit, Earth dominates everything. Communication delays are minimal. Navigation relies on Earth-based systems. Emergency returns are possible. Psychological comfort comes from knowing home is close. The farther we go, the more Earth recedes, and the more exposed we become. This is why space agencies obsess over the phrase Earth independence. A mission that cannot survive without Earth support is not exploration. It is an extension cord, and right now every human mission is plugged in. This is not a pessimistic assessment. It is a precise one. Humanity has made extraordinary progress in building machines that briefly defy gravity. But defying gravity is not the same as escaping dependence. The first wall we cannot ignore is not Mars. It is not distance. It is not even radiation. It is leaving Earth in a way that allows us to live afterward. Until we solve that, not once, not heroically, but routinely, every discussion about traveling farther into space is premature. Earth remains the center of every human spaceflight plan because Earth remains the only place where humans can survive naturally. Orbit is a narrow, artificial exception carved out by engineering. Beyond it lies an environment that does not negotiate. This is the reality hidden behind launch footage and countdowns. Rockets rise. Applause follows. Headlines celebrate another step toward the stars. But the truth is quieter and heavier. Each launch is a reminder of how hard it is to leave and how much harder it is to stay away. So when we ask how far we can travel through space right now, the honest answer begins here, struggling against gravity, burning oceans of fuel, clinging to fragile machines, and never truly escaping the planet below. Earth is not behind us, it is still holding on. And until that grip loosens, the universe will remain farther away than we like to admit. For most of human history, the moon was not a destination, it was a symbol. It governed tides, marked time, inspired myths, rituals, and calendars. It hung in the sky close enough to feel familiar, yet distant enough to remain unreachable. Civilizations rose and fell beneath it, never imagining that one day human footprints would mark its surface. And when that day finally came, it felt like the beginning of everything. In July of 1969, humanity did something no species had ever done before. We left our home world, crossed the void, and stood on another celestial body. The images were grainy, the words were rehearsed, but the meaning was unmistakable. The universe was no longer untouchable. For a brief moment, it felt like the future had arrived early. The moon became proof that distance could be conquered, that gravity could be overcome, that the heavens were not reserved for gods. If we could go there, surely Mars would follow. Surely the planets would open themselves one by one. Surely the stars were only a matter of time. But history rarely unfolds the way it feels in the moment, because the moon was not the beginning of unlimited expansion. It was the edge of what we could barely survive. To understand how far we can travel through space right now, we must understand what the moon missions truly were, not as symbols, but as realities, stripped of romance, stripped of nostalgia, stripped of myth. The Apollo missions were not sustainable exploration. They were controlled gambles. Everything about them was pushed to the limit. The technology, the timelines, the risk tolerance, the human body. The margins were razor thin, and everyone involved knew it. Engineers quietly estimated survival odds that would be unacceptable today. Astronauts signed wills before launch. Mission planners accepted that catastrophe was not just possible, but statistically likely over enough attempts. Apollo worked because failure did not happen, not because the problem was solved. The moon is only about 3 days away. That distance is critical. 3 days of life support, 3 days of exposure, 3 days of mechanical risk. Short enough that systems could be simplified. Short enough that emergency returns were theoretically possible. Short enough that humans could endure the stress. Even then, things went wrong. Apollo 13 came within hours of killing its crew. An oxygen tank exploded, power failed, carbon dioxide levels rose, navigation systems were crippled. The crew survived, not because the spacecraft was robust, but because engineers on Earth improvised under impossible constraints. The mission succeeded by ingenuity and luck, not redundancy. This matters because the moon is the closest place we can fail and still survive. Beyond it, rescue disappears. The moon sits just outside Earth's protective magnetic field. That alone makes it fundamentally different from orbit. Astronauts traveling to the moon are exposed to higher radiation levels, including solar storms that can deliver lethal doses in hours. During Apollo, missions were lucky. A major solar flare during transit, could have killed the crew. There was no shield. There was no escape. Every lunar mission balanced against invisible cosmic violence. And yet, even with all these dangers, the moon remains the maximum distance humans have ever reached. Over 50 years later, no one has gone farther. Not because we forgot how, but because the moon revealed something deeply unsettling. It showed us that going farther is not a linear progression. It is an exponential leap in difficulty. The moon is close enough that missions can be short. Mars is not. A Mars mission takes months just to get there. That changes everything. Life support systems must function for years, not days. Radiation exposure accumulates relentlessly. Psychological stress compounds. Mechanical failures cannot be fixed from Earth in real time. The moon allowed us to pretend that distance was manageable. Mars removes that illusion. This is why the moon has quietly transformed from a stepping stone into a wall. Every plan to go beyond it circles back to the same question. Can humans survive long enough away from Earth to make the journey worth attempting? So far, the answer remains uncertain. The moon itself offers no refuge. It has no atmosphere to protect against radiation, no magnetic field to deflect charged particles, no readily accessible water or breathable air. Temperatures swing violently between extremes. Dust is abrasive, electrostatically charged, and toxic when inhaled. Living on the moon is not colonization. It is permanent crisis management. Every habitat would be a sealed system dependent on constant maintenance. Every failure would be life-threatening. Every supply chain would stretch back to Earth at enormous cost. There is no natural environment to adapt to, only hostility to endure. This is why serious lunar base proposals read more like survival manuals than visions of expansion. They are exercises in how long humans can resist an environment that offers nothing in return. And this leads to a deeply counterintuitive truth. The moon is not easy because it is close. It is hard precisely because it is just far enough away to remove Earth's protection, but not far enough to justify irreversible commitment. The Apollo missions succeeded because they were temporary. Astronauts went, stayed briefly, and left. They did not need to build sustainable systems. They did not need to endure years of exposure. They did not need to solve the hardest problems of space survival. The moment you attempt permanence, the moon becomes far more difficult. This is why, despite renewed interest and modern programs, humanity still treats the moon cautiously. It is no longer a race. It is a test. A place where we confront the limits of our ability to live beyond Earth, not just visit. And so far, the test remains unresolved. Another illusion the moon shattered was speed. It took the Apollo spacecraft 3 days to reach lunar orbit. That seems fast, until you realize it was achieved by pushing chemical propulsion to its practical limits. There is no simple way to go much faster without radically new technology. Faster travel would require exponentially more energy, more fuel, or propulsion methods we do not yet possess. This matters because every extra day in space is danger. Short trips hide long-term problems: bone loss, radiation damage, psychological strain. These are manageable over days. Over months, they become serious. Over years, they become mission-ending. The moon allowed us to ignore this by keeping missions short. Mars does not allow that luxury. This is why, when people ask why we haven't just gone back to the moon regularly, the answer is uncomfortable. We could, but doing so safely, sustainably, and repeatedly is far harder than the public imagines. The Apollo program cost the equivalent of hundreds of billions of dollars. It was powered by geopolitical desperation, not economic logic. Today's space programs operate under different constraints. They must justify cost, minimize risk, maximize return. They must survive political cycles and public scrutiny. And within those constraints, the moon becomes less a triumph and more a reminder of how thin the margin really is. The moon also exposed a psychological boundary. Apollo astronauts spoke later about the profound effect of seeing Earth from space. Small, fragile, alone. It was beautiful, but it was also unsettling. Beyond the moon, that feeling intensifies. Communication delays grow. The sense of isolation deepens. Earth stops feeling close. For humans, proximity matters. Psychological studies of long-duration spaceflight consistently show that isolation, confinement, and distance from Earth strain mental health. Crews experience depression, irritability, cognitive decline, and social breakdown. Even in orbit, with constant contact and near-instant communication, these effects are measurable. Beyond the moon, communication delays become unavoidable. Conversations stretch into minutes. Emergency guidance becomes slower. Crews become more autonomous and more alone. This psychological cost is rarely discussed, but it is as real as radiation. So when we say the moon is humanity's furthest reach, we must be precise about what that means. It is not just the furthest distance traveled, it is the furthest distance at which human survival remains marginally manageable. Beyond it, every risk multiplies. This is why modern plans often frame the moon not as a destination, but as a rehearsal, a place to practice autonomy, to test life support systems, to study long-term exposure, to learn how humans cope when Earth is no longer a constant presence. In other words, the moon has become a mirror. It reflects back the truth we would rather ignore, that space does not open gradually. It opens violently, demanding solutions faster than we can invent them. The moon taught us that we can leave Earth, briefly. It also taught us that leaving Earth changes everything. It stripped away the comforting illusion that progress is automatic. It showed us that one historic achievement does not guarantee another. It revealed that exploration is not a ladder, but a series of cliffs. And standing on the edge of the moon, humanity looked out and realized something quietly terrifying. The universe is not just far, it is farther than we are ready for. So when we ask how far we can travel through space right now, the moon answers honestly. It says, "This is the edge. This is the place where ambition meets biology, physics, and cost, and hesitates." We reached it once by accepting enormous risk. We have not gone beyond it because we have not yet learned how to live there. The moon is not a stepping stone we left behind. It is a warning we are still trying to understand. And until we do, the path forward remains uncertain. Because the distance to Mars is not measured in kilometers. It is measured in everything the moon showed us we still lack. If the moon was humanity's first step away from Earth, then Mars is the first place that asks an unforgiving question in return. Do you actually belong here? For generations, Mars has lived in the human imagination as something almost inevitable. The red planet glows in the night sky like an invitation. It has seasons, polar ice caps, a day only slightly longer than Earth's, ancient riverbeds etched into its surface like scars from a wetter past. It feels familiar in ways no other planet does. And familiarity is dangerous. Because Mars is not Earth-like. It is Earth after everything went wrong. The distance alone should shatter any illusion of simplicity. At its closest approach, Mars is about 56 million kilometers away. At its farthest, over 400 million. There is no straight-line commute. Earth and Mars move constantly, chasing each other around the Sun in an orbital dance that dictates when travel is even possible. Launch windows open roughly once every 26 months. Miss one, and you wait more than 2 years. And once you leave, there is no turning back. A Mars mission is not a journey. It is a commitment to isolation. 6 to 9 months of travel through interplanetary space. No resupply, no rescue, no rapid return. The spacecraft becomes the entire universe of the crew, sealed off from Earth by distance, delay, and physics. Every system must work. Every human must endure. And the environment between here and there is actively trying to kill you. Unlike Earth orbit or even the Moon, the journey to Mars takes place almost entirely outside Earth's magnetic shield. This exposes astronauts to constant cosmic radiation, high-energy particles that slice through DNA, damage cells, and increase cancer risk in ways we still do not fully understand. This radiation is invisible, silent, unstoppable. No current spacecraft provides adequate shielding without becoming impossibly heavy. Water, fuel, and supplies help absorb some radiation, but not enough. A powerful solar storm during transit could deliver a lethal dose in hours. There would be nowhere to hide. Radiation is not a hypothetical problem. It is a guaranteed one. Then there is the problem of the human body. In microgravity, muscles weaken, bones lose density, fluids shift toward the head, altering vision and increasing pressure in the skull. The immune system becomes less effective. The cardiovascular system deconditions. Over months, these changes compound. By the time a crew reaches Mars, they will already be physically compromised. And then they must land. Mars landings are among the hardest feats in spaceflight. The atmosphere is too thin to rely on parachutes alone, yet thick enough to generate extreme heat. Every Mars landing ever attempted has been a high-risk maneuver. Many have failed. Now imagine landing not a robotic probe, but a massive human-rated spacecraft, carrying living people who must survive not just impact, but what comes after. Mars gravity is only about 38% of Earth's, enough to strain weakened bones and muscles, but not enough to restore them. Astronauts would step onto the surface in bodies already altered by months in space, then attempt to live and work in a hostile environment. Mars offers no breathable air, no liquid water on the surface. Average temperatures around 60 degrees C. Global dust storms that can last for months, blocking sunlight and coating everything in fine, abrasive particles. Every breath must be manufactured, every drop of water recycled, every calorie carefully rationed. Mars is not a place you visit, it is a place you survive. And survival changes the meaning of distance. On Earth, distance is measured in miles and hours. In space, it is measured in time without failure. Every additional day multiplies risk. Every extra system increases complexity. Every redundancy adds mass. Every kilogram costs fuel. Every fuel increase demands larger rockets. Every larger rocket increases cost and failure probability. This cascade is why Mars remains out of reach, not because we don't know where it is, but because getting there safely, staying alive and coming back requires solving dozens of interconnected problems at once. No single breakthrough is enough. People often ask why we haven't gone to Mars yet, as if it were simply a matter of willpower or funding. But Mars is not waiting patiently. It is indifferent. It demands answers to questions we are still struggling to ask correctly. How do you protect humans from radiation for years? How do you maintain mental health in extreme isolation with communication delays of up to 22 minutes one way? How do you repair critical systems when replacement parts are millions of kilometers away? How do you land safely, then launch again from a planet with no infrastructure? How do you bring people home without killing them on return? Right now, we do not have complete answers. That does not mean Mars is impossible. It means Mars is not yet survivable. Even optimistic projections acknowledge this. Proposed Mars missions rely heavily on assumptions about technologies that must work perfectly the first time. In situ resource utilization, advanced life support recycling, autonomous systems capable of handling emergencies without Earth's guidance. Each of these is plausible. None are proven at the required scale, and Mars does not forgive testing errors. One failed oxygen recycler, one unfixable leak, one psychological breakdown. In orbit, these are emergencies. On Mars, they are deaths. This is why many experts argue that a Mars mission today would be less like exploration and more like a calculated gamble with human lives. The kind of gamble Apollo once represented, but stretched across years instead of days. The difference is that Apollo's risk was visible and short. Mars's risk is invisible and cumulative. There is also the question no one likes to ask openly. What if something goes wrong after landing? A Mars crew cannot simply leave. Return windows are as strict as departure windows. Fuel production plans rely on equipment that must function flawlessly in an alien environment. If launch capability fails, the crew may be stranded indefinitely. Mars has no backup. This reality reframes the question of how far we can travel through space right now. We can send machines to Mars routinely. Rovers, landers, orbiters. They succeed because they do not need air, mental health, or hope. Humans are different. Our biology evolved for Earth. Our psychology evolved for community and proximity. Space strips away both. Even communication becomes a burden. Conversations slow to a crawl. Real-time support vanishes. Crews must solve problems alone, knowing that Earth cannot help quickly, if at all. This isolation is not just technical, it is existential. Astronauts already report feeling detached from Earth after weeks in orbit. Mars would magnify that detachment beyond anything humans have experienced. The planet would hang in the sky like a distant star. Home would become an idea rather than a place. And ideas cannot provide oxygen. So when people say Mars is the next step, they are simplifying something vast and brutal. Mars is not a step. It is a leap across a chasm filled with unanswered questions. This is why, despite constant announcements, Mars remains in the future tense. Plans shift, timelines move, architectures are revised. The goal remains, but the reality resists. Not because we lack courage, because we lack margin. Every human spaceflight beyond Earth orbit operates with thin margins. Apollo survived on them. Mars would consume them entirely. There would be no slack, no buffer, no room for error. And yet, the dream persists. Because Mars represents more than distance. It represents the possibility that humanity is not confined to one fragile world, that we can adapt, that we can endure. That extinction is not inevitable. This is why Mars remains both a promise and a warning. It promises a future where humans are no longer bound to Earth alone. But it warns us that the universe does not care about our aspirations. Right now, Mars sits at the edge of what we can imagine, but just beyond what we can safely do. It is close enough to haunt us, far enough to defeat us. So how far can we travel through space right now? We can reach orbit reliably. We can touch the moon briefly. We can send robots across Mars's surface. But sending humans to Mars and bringing them back alive remains a problem unsolved. Not because we lack rockets, not because we lack ambition, but because space is not conquered by desire. It is endured by preparation. And Mars is waiting patiently for us to learn that lesson. Mars feels far until you realize what comes after it. Beyond the red planet, the solar system does not gradually unfold. It opens violently, stretching outward into distances so vast that the word travel begins to lose its meaning. The inner planets lull us into a false sense of scale. Mercury, Venus, Earth, Mars. They cluster close to the sun, close enough that months of travel can bridge the gap. Then you pass Mars, and the universe changes. Between Mars and Jupiter lies the asteroid belt, often imagined as a dense minefield of tumbling rocks. In reality, it is mostly empty space, but that emptiness is the problem. The asteroid belt marks the boundary where human spaceflight stops being about missions and starts being about endurance beyond any precedent. To reach the asteroid belt, a spacecraft must travel far longer than any crewed mission in history. Even at high speeds, the journey takes years. Years of radiation exposure, years of isolation, years of mechanical systems operating without failure. And that is just to arrive. The asteroid belt offers no refuge, no shelter, no breathable air, no gravity worth mentioning. Any human presence would be confined to spacecraft or artificial habitats, floating endlessly in darkness. Repairs would be constant, psychological strain relentless. But the belt is not the real barrier. Jupiter is. Jupiter is so massive that it reshapes the solar system around it. Its gravity dominates the outer planets. Its radiation belts are lethal. A human approaching Jupiter without extraordinary shielding would receive fatal radiation doses in days or hours. Robotic spacecraft survive Jupiter by limiting exposure and accepting damage. Humans cannot. Even if radiation was somehow solved, the distance alone is crushing. Jupiter is, on average, over 600 million kilometers from Earth. Travel times stretch into multiple years one way. Communication delays grow to nearly an hour round trip. Earth becomes a memory, not a presence. And Jupiter is still just the beginning. Saturn, Uranus, Neptune, each one farther, colder, darker than the last. Sunlight weakens until it is little more than a bright star. Solar power becomes ineffective. Nuclear systems become mandatory. Supply chains vanish entirely. At these distances, rescue ceases to be a concept. No human mission can rely on Earth support beyond Mars. Every system must be autonomous, every decision final, every failure permanent. This is where the idea of how far can we travel collapses into something more sobering. How long can we survive without Earth? Right now, the answer is measured in months, not decades. Even the most optimistic life support systems struggle with long-term reliability. Closed-loop ecosystems fail in subtle ways. Microbes evolve, filters clog, materials degrade. Tiny inefficiencies accumulate until systems collapse. Earth hides these problems by constantly correcting them. Space does not. Then there is gravity, or rather, the lack of it. Long-term exposure to microgravity fundamentally alters the human body. Artificial gravity through rotation is theoretically possible, but has never been tested at scale for years with humans. Engineering such habitats adds mass, complexity, and risk far beyond current capabilities. And even if we could solve the engineering, we face a deeper truth. Human beings evolved to live under a sky. Psychological studies from submarines, Antarctic stations, and space missions all point to the same conclusion. Isolation erodes cognition. Confinement amplifies conflict. Distance from nature degrades mental health. Beyond Mars, there is no horizon, no weather, no living world outside the walls, just machinery and vacuum. The farther you go, the more the mission becomes less about exploration and more about psychological survival. Crews would need to function flawlessly for years under stress no human society has ever experienced voluntarily. This is why even discussions of human missions to the asteroid belt or outer planets are rare. They are not dismissed because they are uninteresting, but because they are currently meaningless. We can imagine them, we can design them on paper, but imagination is cheap. Survival is not. The harsh reality is this: every step farther from Earth multiplies problems rather than adding new opportunities. Distance compounds radiation, time compounds risk, isolation compounds failure. And there is no natural stopping point where things get easier again. The outer solar system offers wonders: ringed planets, icy moons, subsurface oceans. But those wonders are locked behind distances that demand technologies we do not yet possess. Faster propulsion, better shielding, artificial gravity, fully autonomous life support. Without these, human presence remains impossible. This is why robotic explorers dominate the outer solar system. Machines do not need air. They do not suffer loneliness. They do not care if a signal takes hours to arrive. They can hibernate, fail silently, and still be considered successes. Humans cannot. The idea of traveling to Jupiter, Saturn, or beyond is often framed as a question of ambition. But ambition is not the limiting factor. Biology is. Our bodies are fragile. Our minds are delicate. Space is neither. This is the core truth that Section 5 reveals. The solar system is not arranged for human expansion. It is arranged for Earth-based life, with everything else hostile by default. Mars tempts us because it is barely survivable. The rest of the solar system does not even pretend. So how far can we travel through space right now? Not to the asteroid belt, not to Jupiter, not to Saturn's moons. We can send machines, we can send signals, we can send ideas, but humans remain bound to a narrow bubble around Earth, a fragile shell of distance where our biology still functions and help is still possible. Beyond that shell lies a universe that does not negotiate. And this brings us to an uncomfortable realization. Distance is not the true enemy. Time is. The longer humans remain away from Earth, the more everything unravels. Systems fail, bodies weaken, minds strain. The universe does not attack, it simply waits. Which is why, for now, the outer solar system remains untouched by human hands. Not because we lack the courage to go there, but because we lack the ability to stay alive long enough to matter. And until that changes, the stars beyond Mars will remain what they have always been: visible, reachable in theory, and completely out of reach in practice. Every civilization that has looked up at the night sky has dreamed of faster-than-light travel, faster than the sun's photons, faster than the cosmic clock itself, faster than the cold, indifferent vacuum that separates stars from one another. It is the ultimate question of space travel. Can we outrun the universe? And yet, for everything humanity has ever achieved in space, we have never approached this limit. Not once. Not even close. Light is the speed limit. The universe does not negotiate. This is why Section 6 is not about rockets, or life support, or Mars. Those are challenges that, given time, engineering, and resources, might be overcome. This section is about absolute barriers, barriers that are neither political nor economic nor biological, barriers built into the very fabric of reality. The speed of light, denoted as c, is 299,792 kilometers per second. That number is meaningless in ordinary life. It is so fast that it seems infinite. Light travels from the Moon to Earth in just over 1 second. It crosses the distance from Earth to the Sun in about 8 minutes. It reaches Pluto in roughly 5.5 hours. Yet even this speed, the ultimate cosmic constant, is painfully slow when measured against the distances between stars. The nearest star system, Alpha Centauri, is 4.37 light-years away. A year, for reference, is 365 days. A light-year is the distance light travels in that span. For anything moving slower than light, which is everything with mass, this distance stretches into decades, centuries, or millennia. Rockets travel orders of magnitude slower than light. Even the fastest spacecraft ever built, the Parker Solar Probe, reaches 0.064% of light speed. At that pace, reaching Alpha Centauri would take over 6,600 years. That is longer than recorded human history, longer than civilizations have risen and fallen, longer than a human lifetime can encompass. This is the first truth of interstellar travel. The cosmos is enormous beyond comprehension. Even small gaps are vast when measured in the time required to cross them. Science fiction often glosses over this. Warp drives, hyperspace, wormholes, stories that make the journey feel manageable. They compress years into hours, light years into minutes. But these are not solutions. They are imagination masquerading as science. Nothing in physics currently allows faster than light travel. Not for particles, not for spacecraft, not for information. Even attempts to cheat relativity encounter insurmountable problems. The more you approach light speed, the more mass increases. Energy requirements grow without bound. Time dilates. To travel at light speed, an object with mass would require infinite energy. Infinite. A concept that is comprehensible mathematically, but utterly impossible practically. And yet, relativity offers a tantalizing insight. Time is not universal. For humans traveling at a significant fraction of light speed, time passes differently than for those left behind. This is not science fiction. It is verified physics. Known as time dilation, it means that astronauts could theoretically age slower than people on Earth. Travel 90% of light speed toward a distant star, and decades might pass on Earth while only a few years pass for the crew. This creates a profound and uncomfortable reality. Even if we could achieve near light speed travel, we would never return to the Earth we left. Decades or centuries would have passed. Civilization would have moved on. Loved ones would be gone. Humanity itself might look entirely different. This is the second truth of interstellar travel. Reaching the stars is not only a question of speed, it is a question of isolation from the very time you know. Energy is the third truth, and it is absolute. Propulsion capable of approaching light speed is not incremental, it is staggering. Even theoretical concepts like antimatter propulsion require storing and managing energies that could devastate entire cities if released uncontrolled. Every kilogram of payload multiplies the energy demands exponentially, and every extra kilogram is essential for survival: food, water, shielding, life support, redundancy. Interstellar travel is not just a journey through space, it is a fight against physics for every second of life. Radiation again becomes a limiting factor. The interstellar medium is not empty. Cosmic rays permeate space. Shielding against them for journeys spanning decades is currently beyond our capabilities. Even small amounts of matter at near-light speed can have catastrophic consequences. Tiny dust particles hitting a spacecraft at 90% of light speed carry the energy of high explosives. Every calculation compounds, every risk multiplies, every margin disappears. Which is why, despite centuries of dreaming, no human has traveled beyond the solar system. Voyager 1, launched in 1977, is humanity's furthest reaching object. It has left the heliosphere, the sun's protective bubble, but is traveling at only 17 kilometers per second, or 0.05% of light speed. At that rate, it will take over 70,000 years to reach even the nearest star. No life on board, no human observers, only silence and radio signals carrying echoes of the past. This is the third hard truth. Distance, speed, and survival conspire to confine humanity to a tiny bubble of space-time. And yet, humans are restless. We continue to imagine faster methods: nuclear pulse propulsion, fusion engines, breakthrough starshot, tiny spacecraft accelerated by lasers to 20% of light speed. Each idea pushes the envelope. Each one faces monumental challenges: materials capable of withstanding the stresses, power supplies that do not fail, systems that operate autonomously for decades, communication across vast distances. Even these theoretical breakthroughs do not solve the human problem. A 20% light-speed spacecraft with humans aboard would still require years to reach the nearest stars. Radiation would be relentless. Life support would need to function without repair for longer than any civilization has existed. The physics does not bend for ambition. It does not negotiate with desire. This is why the outer solar system and the stars beyond are more than distances. They are mirrors reflecting the limits of human biology, technology, and psychology. Our minds dream of interstellar travel. Our rockets reach only a fraction of that distance. Our bodies cannot survive what lies in between. Time itself conspires against us. Light speed acts as a tether, connecting distant objects but preventing them from being reached in a human lifespan. Faster than light travel remains a fantasy, a poetic way to skirt around physics we do not yet understand. Even communication is bounded. Messages to Mars take minutes to travel, to Jupiter, hours, to Alpha Centauri, years. Any civilization attempting interstellar contact faces delays that render real-time guidance impossible. Even if humans could survive the trip, they would arrive as strangers in a universe that moved on without them. This is the fourth truth. Cosmic distances are measured not in kilometers, but in consequences, and consequences are brutal. Every attempt to accelerate beyond these limits encounters the same reality. The universe enforces constraints. Speed is capped. Time is relative. Energy is finite. Survival is fragile. The cosmos does not reward ambition alone. Yet paradoxically, this limitation is also a gift, because by understanding the absolute barriers imposed by light, time, and energy, humanity gains clarity. We can plan realistically. We can prioritize achievable targets. We can optimize survival in the solar system before dreaming of the stars. We can recognize the difference between hope and physics. Even light itself carries a lesson. It illuminates distances, reveals structure, but reminds us of scale. What we see when we look at distant stars is already history. Many of the stars visible tonight are long dead. Their light reaches us only now because the cosmos is vast. We are, in essence, looking at ghosts. And in that realization lies humility. The universe is older, larger, and less accommodating than we like to imagine. Light speed limits our reach. Time dilation offers only partial reprieve. Energy requirements make most interstellar ambitions theoretical at best. In practical terms, human travel beyond the solar system is impossible with current technology. Not because we lack courage, imagination, or determination, but because the physical laws governing the universe are absolute. This section is a pause, a reflection before the final chapters of distance and survival. It shows that no amount of planning can erase certain boundaries. No rocket can outrun light. No spacecraft can ignore time. No human can survive the vacuum unprotected for more than a few seconds. Yet we continue. We always will. Because even knowing the limits, humanity's instinct is to reach farther, to press the boundaries of knowledge, to challenge the walls of the possible. And the universe does not move for us. It waits, indifferent, implacable, infinite. Space is often described as hostile. That is true. Vacuum, radiation, temperature extremes, micrometeoroids traveling at tens of kilometers per second. These are the dangers that dominate headlines, the ones engineers obsess over, the ones that inspire heroic imagery of astronauts defying death. But for human beings, the hardest enemy is always themselves. Even on missions as short as a week in orbit, astronauts experience the subtle unraveling of their bodies and minds. On missions lasting months, the effects compound. By the time humans travel beyond the moon, into multi-month or multi-year journeys, the human factor becomes not just a challenge, it becomes the limit. The boundary that defines how far we can realistically travel. Every human mission ever attempted offers lessons in survival under extreme conditions. Every failure, near miss, and success illuminates the fragile balance between biology and technology. The Apollo missions taught us about isolation, stress, and the consequences of prolonged exposure to radiation. Skylab and the Mir space station revealed how microgravity affects muscles, bones, and vision. The International Space Station has pushed the envelope on nutrition, sleep cycles, and psychological stability. And the lessons are unambiguous. Space is not a neutral environment. It actively erodes human capability. Let's start with the body. Microgravity is a form of slow, relentless decay. Bones lose density at a rate of 1 to 2% per month. Muscles atrophy. Cardiovascular systems weaken. The inner ear, which governs balance, becomes confused, leading to dizziness and disorientation. Fluids shift toward the head, altering intracranial pressure and even vision. These effects accumulate, and while exercise can mitigate them, it cannot fully prevent long-term deterioration. Imagine a Mars mission lasting 9 months just to arrive, with a similar journey back. By the time humans set foot on the surface, they will have already begun a decline in strength, coordination, and bone integrity. Walking in Mars gravity will be a struggle. Tasks requiring precision or stamina will be far more dangerous. Every movement could be accompanied by fatigue or injury. Nutrition compounds the problem. In microgravity, the body's metabolism changes, appetite diminishes, nutrient absorption shifts. Long-duration missions cannot rely solely on Earth-like diets. Food must be compact, shelf-stable, and nutritionally dense. The monotony of such diets affects morale. Psychological resilience is intimately tied to nutrition, yet the more distant the mission, the harder it is to ensure adequate sustenance. Sleep is another battlefield. Without natural day-night cycles, the circadian rhythm begins to drift. Sleeping in microgravity feels different. Hours can pass without rest, or rest can become fragmented. Cognitive performance suffers. Decision-making degrades. Delays in judgment, even small ones, can cascade into catastrophic consequences in environments where error is lethal. Radiation, too, is invisible, cumulative, and unforgiving. Outside Earth's magnetic field, galactic cosmic rays bombard every cell. Solar particle events can deliver doses capable of inducing acute radiation sickness. Shielding adds mass, complexity, and cost, but even then, it can never fully eliminate the risk. Every kilometer traveled beyond Earth increases exposure. Every month compounds it. Even if astronauts survive the journey, long-term cancer risk is significant. All of these physical stresses converge to a single point. Human endurance has hard limits. Technology can compensate, mitigate, and buffer, but biology cannot be rewritten. Yet physical limits are only half the story. The other half is mental. Isolation and confinement are potent adversaries. In orbit, crews live in spaces measured in tens of meters. They share corridors, bathrooms, and even air with the same people for months on end. Conflict is inevitable. Tensions rise over minor irritations, differences in habits, and miscommunications. Social dynamics can erode cohesion, reduce cooperation, and increase risk. Mars magnifies this problem. Imagine 9 months in cramped quarters, with no escape, no new faces, no fresh air. Imagine not being able to step outside for relief. Imagine small conflicts escalating when every mistake carries life or death consequences. Even highly trained crews are not immune. Antarctic stations and submarines offer Earth-based analogues. In isolation, mood disorders rise, sleep disturbances worsen, cognitive function declines, group cohesion fractures under stress. Now multiply these effects across months or years in deep space, with communication delays stretching support from Earth into hours, and the picture becomes stark. Psychology is not theoretical, it is practical, immediate, and dangerous. A minor breakdown, left unchecked, can jeopardize the entire mission. Decision-making, problem-solving, and morale are as critical as oxygen or water. Humans may be physically capable, but mental fragility can end a mission faster than any technical failure. And then there is the existential strain. Distance from Earth is not just spatial, it is temporal. The further one travels, the longer communication takes. Messages that would take seconds in orbit now take minutes, hours, or years. By the time a response arrives from mission control, the context may have changed. Immediate guidance is impossible. Crews must make life or death decisions entirely alone. This autonomy is necessary, but it is also a psychological burden. The sense of detachment from home intensifies with every kilometer. Families, friends, and the familiar rhythms of Earth become memories, not anchors. Crews experience a profound form of temporal isolation. By the time they arrive at their destination, they may have aged years while Earth has aged decades. They become strangers, not only to their environment, but to their own civilization. This is why long-duration missions test resilience as much as engineering. They demand not just physical robustness, but mental and social agility. They require the ability to endure monotony, uncertainty, danger, and isolation with equanimity. They require emotional intelligence as critical to survival as oxygen. Consider communication delays in more detail. A Mars mission has a round-trip communication delay of up to 44 minutes. That means astronauts cannot receive immediate guidance in emergencies. They must troubleshoot life support failures, medical crises, or navigation errors entirely on their own. Every decision is amplified by stakes. Errors that would be minor on Earth become catastrophic in space. Even on Earth, humans struggle with delayed feedback. In space, these delays magnify stress and uncertainty. Confidence erodes, anxiety rises. Decision fatigue sets in. Long-term missions require not only individual resilience, but team dynamics optimized for isolation and stress. Medical emergencies present another challenge. No surgeon can assist mid-transit. No hospital exists beyond the spacecraft walls. Every potential injury, illness, or mental health crisis must be anticipated, planned for, and managed autonomously. Supplies are finite. Procedures must be simplified. Risk cannot be transferred. It must be borne entirely by the crew. The longer the mission, the narrower the margin for error. A medical complication that is minor on Earth becomes potentially fatal in transit. Every day beyond the moon adds cumulative risk to both physical and psychological systems. This is why Mars and beyond are not merely logistical challenges. They are human limits expressed spatially. Technology can carry us far, but only biology can make the journey survivable. And biology has not yet evolved for life outside a planet with gravity, atmosphere, and ecosystem. Sleep, nutrition, radiation, bone density, muscle mass, psychological resilience, social cohesion, all these factors intersect. Failure in any one domain jeopardizes the mission. Success requires mastery across them all. This intersection of physical and psychological constraints defines what Section 7 calls the human factor, the point at which biology, technology, and distance converge to determine the ultimate limit of travel. Beyond this point, even the most sophisticated spacecraft cannot compensate for human vulnerability, and yet the human factor is not merely a limit. It is also a source of possibility. Humans are adaptive. We innovate, we endure, we learn from extreme environments on Earth, submarines, polar stations, long-duration flight simulators, and apply those lessons to space. Behavioral strategies, training regimens, psychological monitoring, redundancy in critical tasks, all these increase the margin of survival, but they do not eliminate risk. Even with perfect planning, human fragility is the largest unknown in interplanetary travel. Systems may function flawlessly, but human error, fatigue, or breakdown can still threaten survival. Every extended mission beyond Earth orbit must account for the fact that crew survival is the ultimate constraint. This is why current human space travel remains limited. We can survive weeks to months in orbit. We can manage brief missions to the moon. But beyond that, the cumulative stresses, physical, psychological, social, define a boundary we have yet to cross. Mars is possible in theory, but only with exceptional preparation, risk acceptance, and mitigation. The outer planets? They are effectively unreachable for humans today. The human factor teaches a profound lesson. Exploration is not only a question of distance or propulsion or technology. It is a question of what humans can endure. The universe imposes hard limits, and those limits are often psychological, not mechanical. Even the most advanced spacecraft cannot carry hope, courage, or mental resilience as cargo. These are human qualities, fragile and finite, and they will determine whether any journey beyond the moon succeeds or fails. So when we ask, how far can we travel through space right now? The answer must include a qualification. The farthest distance we can reliably send humans is not determined by rockets or fuel. It is determined by our ability to survive the stress of isolation, radiation, confinement, and time. Until we solve the human problem as thoroughly as the technological problem, every journey beyond Mars remains theoretical. Every star beyond light years a dream. The human factor is both our limitation and our frontier. Master it, and we may reach farther than we ever imagined. Fail to master it, and the universe will simply leave us behind. Because space does not negotiate, it does not wait, it does not forgive, and survival is never guaranteed. The solar system is vast, that is obvious, but it is also deceptive. Up close, the inner planets, Mercury, Venus, Earth, Mars, seem like stepping stones, a series of milestones humans might traverse with patience, ingenuity, and courage. But as we peer farther outward, the apparent continuity dissolves. Space does not gradually become harder to cross. It becomes exponentially hostile, indifferent, and vast beyond comprehension. Why are the outer planets and their moons unreachable today, and what would it take to go there? The first boundary lies in the asteroid belt. Popular imagination often depicts it as a chaotic minefield of rocks, spinning and colliding with violent regularity. Reality is more subtle and cruel. The asteroids are widely spaced, but but their environment is unforgiving. Gravity is negligible. Temperatures swing wildly. Radiation, while not as intense as Jupiter's magnetosphere, still imposes a chronic hazard. Human presence here would be confined to spacecraft or artificial habitats. Any extended mission would require constant life support, radiation shielding, and the ability to repair every system independently. Unlike Mars, there is no hope of in situ resources that are easily accessible. Water ice exists, but it is locked in tiny pockets, scattered across millions of kilometers. Any mining or processing requires infrastructure humanity does not yet possess. Beyond the asteroid belt lies Jupiter, the first giant of the solar system. Jupiter is enormous. Its gravity well is unmatched in the solar system, second only to the Sun. Orbiting Jupiter is a radiation storm of unprecedented intensity. The planet's magnetic field traps energetic particles, forming radiation belts millions of times stronger than Earth's Van Allen belts. For a human, approaching Jupiter without heavy shielding would be instantly lethal. Every centimeter of spacecraft material matters. Every joule of energy devoted to propulsion or life support competes with mass needed for radiation protection. Jupiter is a world where the concept of getting close is meaningless unless accompanied by extreme technological solutions. And yet, Jupiter's moons, Io, Europa, Ganymede, Callisto, offer some of the solar system's most tantalizing possibilities. Europa's ice shell conceals an ocean that could harbor life. Ganymede possesses its own magnetic field. Callisto, distant and geologically stable, is perhaps the only candidate for a long-term human base, albeit far beyond any current capability. The distances alone are daunting. Travel to Jupiter from Earth takes years. Communication is delayed by tens of minutes. Even a perfectly functioning spacecraft leaves humans vulnerable to minute errors, mechanical failures, or cosmic events. Every day adds cumulative risk. Saturn, the next giant, adds new dimensions of danger. Its iconic rings captivate the imagination, but they are also a hazard for orbiting spacecraft, an environment of icy particles moving at high velocities. Saturn's moons, particularly Titan, present intriguing possibilities for exploration. Titan's thick atmosphere, lakes of liquid methane, and organic-rich surface make it one of the most Earth-like environments in terms of chemical complexity. Yet, it is also nearly 1.4 billion kilometers from Earth at its closest approach. Reaching Titan is not a question of ambition, it is a question of survival. Even with a decade-long mission, spacecraft must operate autonomously, shields must protect against radiation, and every life support system must function flawlessly. For humans, Titan is not a destination. It is an existential experiment. Uranus and Neptune push these challenges to the extreme. These ice giants are so far that solar energy becomes negligible. Missions must rely entirely on nuclear or exotic propulsion systems. Temperatures plunge to near absolute zero. Radiation is lower than Jupiter or Saturn, but isolation and travel time dominate every calculation. Communication delays stretch hours, then days. Even small contingencies cannot be addressed in real time. Beyond Neptune lies the Kuiper Belt, a vast frozen repository of ancient bodies. Pluto, once a planet, now the most famous Kuiper Belt object, is emblematic of this region. Its icy plains, mountains, and tenuous atmosphere captivate imaginations, but to reach Pluto requires years of travel. To survive there requires technologies humanity has only begun to develop. There is no atmosphere breathable by humans. There is no energy readily available from the sun. Radiation is constant. Temperatures average 229 degrees Celsius. The Kuiper Belt is not hospitable. It is a cold testament to the limitations of human reach. It reminds us that distance is only one factor. Time, energy, and survivability compound, forming an exponential barrier that cannot be bypassed. Even beyond the Kuiper Belt, in the scattered disk and Oort cloud, objects drift alone in near-total darkness. These regions are the nursery of comets, the remnants of the solar system's formation. They are beautiful, scientifically invaluable, but utterly inaccessible. Human presence here is a dream tethered by the harsh realities of physics, biology, and time. And yet, the solar system tempts us. Its moons contain water ice, its gas giants harbor chemical mysteries, its outer bodies preserve records of the solar system's formation. Robotic explorers can reach them. Human explorers, at this time, cannot. This is where the limits of current human space travel become clear. Our ability to survive long durations in deep space defines the boundary of exploration. Propulsion alone is insufficient. Radiation protection alone is insufficient. Life support alone is insufficient. All must function together flawlessly for years, and humans must endure the mental, physical, and social stresses of isolation. Even with current propulsion systems, a manned mission to the outer planets is beyond reach. Chemical rockets, the backbone of space travel, are too inefficient for the journey. Nuclear thermal rockets, fusion concepts, and ion drives improve speed, but not enough to compress travel time into tolerable spans for human survival. Autonomy becomes the final, inescapable requirement. At these distances, Earth cannot intervene quickly. Crews must act independently, repair critical systems, and make life or death decisions alone. Every redundancy increases mass and complexity. Every kilogram of fuel or shielding competes with the mass of food, water, and crew accommodations. Even for robotic missions, the outer solar system is unforgiving. Voyager, Cassini, Juno, New Horizons, each success relied on meticulous planning, decades of patience, and constant monitoring from Earth. For humans, the margin for error is zero. The psychology of these distances compounds the problem. Astronauts cannot rely on immediate communication. Time dilation is negligible at these velocities. But the perception of distance magnifies isolation. Months or years pass with only delayed messages from Earth, reinforcing the psychological strain of confinement and distance. Radiation remains a relentless threat. Jupiter and Saturn dominate the inner edge of this zone, but beyond them, cosmic rays penetrate even the most well-shielded spacecraft. Long-duration missions require mass-intensive shielding that challenges propulsion capabilities. Every solution introduces new risks, creating a web of constraints that is nearly impossible to balance. And finally, survival itself is no guarantee of meaningful exploration. To function effectively in these environments, humans must maintain not only life, but also capability. Physical degradation, cognitive decline, or psychological collapse reduces the ability to work, repair systems, and conduct science. Survival without functionality is survival without purpose, a sobering consideration for any mission planner. The outer solar system, therefore, defines the current human boundary in space. Inner planets can be visited with risk management, preparation, and advanced life support. Mars remains the farthest human achievable goal within the foreseeable future. Beyond that, the solar system becomes a test of endurance rather than exploration, a region where the laws of physics, biology, and psychology converge to impose an immutable barrier. And yet, humanity is compelled to look outward. Robotic missions, orbital telescopes, and remote sensing allow us to study these distant worlds, learn from them, and dream. They serve as placeholders for human ambition, reminders that while the solar system is vast and often hostile, it is also a laboratory for understanding our limits. Every outer planet, moon, and asteroid is a challenge in a practical sense, a barrier in an existential sense, and a source of wonder in every other sense. They teach us humility. They teach us patience. They teach us that space is not conquered by desire alone, but by preparation, endurance, and respect for the laws of the universe. In the end, this reveals a clear truth. The solar system has zones of accessibility and zones of impossibility, defined not by imagination, but by human capability. The inner planets invite exploration. The outer planets warn us of the limits of life, distance, and survival. Our reach ends where time, energy, and biology intersect to form an immutable boundary. And within that boundary lies the space humans can truly call their own. Beyond it lies the domain of machines, ideas, and dreams, but not yet the domain of flesh and blood. Every night, the stars appear as tiny pinpricks of light, serene and unchanging. They are distant companions, silent witnesses to Earth's brief history. Yet these points of light are profoundly misleading. They are not near, they are not easily reachable, and they are not forgiving of human impatience. The nearest star system to Earth is Alpha Centauri, a trinary system composed of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Proxima Centauri, a red dwarf, lies 424 light-years away. To comprehend this distance is to confront the cosmic scale. 1 light-year is the distance light travels in a year, about 946 trillion kilometers. Multiply that by 424, and suddenly the distance from Earth to Proxima Centauri is no longer abstract. It becomes incomprehensible. Current spacecraft would take tens of thousands of years to traverse this distance. Voyager 1, humanity's furthest traveling object, launched in 1977, moves at 17 kilometers per second. At that pace, reaching Proxima Centauri would take more than 70,000 years. To put that in perspective, humans have been building civilizations for roughly 10,000 years. A journey to the nearest star exceeds the entire span of human civilization multiple times over. This is the first truth of interstellar travel. The stars are not just far, they are overwhelmingly far. Yet physics offers a tantalizing loophole: near light speed travel. According to Einstein's theory of relativity, as objects approach the speed of light, time slows for them relative to observers at rest. For astronauts traveling at 90% of light speed, decades could pass on Earth, while only a few years pass for the crew. This is not science fiction, it is measurable, verifiable physics. Time dilation is a known phenomenon, tested in particle accelerators, atomic clocks, and satellite systems. Yet it comes at a cost. Accelerating to near light speed requires energy that is currently inconceivable. Every kilogram of spacecraft mass increases the required energy exponentially. Propulsion capable of sustaining such speeds for years or decades is beyond today's engineering. And even if we solved propulsion, the dangers are still enormous. Cosmic rays, micrometeoroids, and interstellar dust become lethal at near light speeds. A particle the size of a grain of sand colliding with a spacecraft, traveling 90% of light speed, would release energy equivalent to a small bomb. Shielding against such hazards adds mass, further compounding energy requirements. This is the second truth of interstellar travel. The universe is actively hostile, and speed amplifies the danger. Yet the human mind cannot resist. We imagine colonizing Proxima Centauri b, a planet orbiting the red dwarf in the habitable zone. Its discovery in 2016 fueled dreams of interstellar settlement. Could humanity build a generation ship, launch into the void, and arrive centuries later to terraform a new world? In theory, perhaps. In practice, the challenges are staggering. Generation ships face biological, mechanical, and psychological barriers. Multiple human generations would live and die aboard a vessel isolated from Earth. Systems would need to operate autonomously for centuries. Repairs would be impossible without infinite redundancy. Social structures would need to endure the stress of confinement, monotony, and existential awareness of being permanently severed from home. Even the slightest failure could doom the entire population. Cryogenic sleep has been proposed as an alternative, but human hibernation remains untested at such durations. Suspending life for decades or centuries introduces medical, ethical, and engineering uncertainties. Even if technically possible, the risk of complete system failure remains high. Meanwhile, communication becomes meaningless. At 4 light-years away, messages take 4 years to travel one way. Guidance from Earth is effectively non-existent. Crews must be entirely self-sufficient, making decisions without real-time oversight. This isolation magnifies every challenge. Even with perfect technology, survival is not guaranteed. Systems degrade, supplies run low, psychological stress accumulates. The farther from Earth, the less room there is for error. And beyond Proxima Centauri lies the rest of the galaxy. The Milky Way contains roughly 400 billion stars. Distances between them are measured in light years, and travel times with foreseeable technology stretch into thousands or millions of years. The human lifespan, even extended by advanced medicine, cannot bridge these gaps. This is the third truth of interstellar travel. Our biology and civilization are ephemeral, but the universe is eternal. Stars live for billions of years, but humans exist for mere decades. Civilization is a blink. Exploration is constrained not only by physics, but by the limits of life itself. Robotic exploration becomes the only practical pathway. Probes can endure decades of travel. They require no life support. They can hibernate or operate autonomously, carrying cameras, sensors, and instruments across vast distances. Missions like Voyager and New Horizons are early examples. They provide the closest humans can currently come to interstellar travel. Presence without flesh, knowledge without movement. Yet even robotic missions face limitations. Signal strength decreases with distance. Delays increase to years for interstellar distances. Power sources decay over time. Instruments degrade. Even machines are vulnerable in the void. The farther the mission, the more patience, redundancy, and foresight it demands. This is where Section 9 confronts a profound realization. Human reach is defined not by ambition, but by endurance. The stars invite exploration, but the universe does not yield to desire alone. To reach them, we must reconcile physics, biology, and psychology in a way humanity has not yet done. Consider also the practical implications of interstellar travel. Supplies, energy, and propulsion are not merely engineering problems. They are existential limits. Food cannot be grown without ecosystems spanning decades. Water must be recycled perfectly. Energy must be sustained without resupply. Even minor errors compound over time. The farther the distance, the less margin exists for failure. The stars are, in effect, natural barriers. They are points of light in a void that cannot currently be crossed by humans. They are reminders that ambition alone does not equal feasibility. They are the ultimate horizon, beyond which humanity's reach is constrained by the laws of the cosmos. And yet, the human mind cannot rest. Imagination thrives on the unreachable. We design theoretical propulsion systems, antimatter engines, fusion drives, laser sails. We calculate speeds approaching a fraction of light. We debate cryogenic sleep, suspended animation, and generation ships. Every idea is an attempt to bypass the constraints imposed by reality, to stretch human presence across cosmic distances. Even so, this emphasizes that the gap between theory and practice is enormous. Energy requirements grow exponentially with speed. Radiation hazards scale with velocity. Time stretches for travelers and observers alike. Life support must function without interruption for decades. Isolation challenges both mental and social resilience. Every variable interacts, creating a problem that is as much human as it is technological. Distance, then, is only one metric. Survival is another. Viability is the third. Humanity can imagine reaching Proxima Centauri, but we cannot survive the journey with current technology. We can send messages and robotic explorers, but flesh and blood remain tethered to the solar system. Even if we could reach the nearest star, the question remains, what would we find there? Exoplanets orbiting Proxima Centauri may exist in the habitable zone, but conditions are likely extreme. Red dwarfs flare unpredictably, bombarding planets with radiation. Magnetic fields may be weak. Atmospheres could be stripped. The challenges of colonization would dwarf the journey itself. The universe does not reward bravery alone. It rewards preparation, endurance, and adaptation. Exploration beyond the solar system is a question not just of distance, but of survival, physics, and the capacity to endure isolation across decades or centuries. Even now, as humanity dreams of interstellar travel, we are constrained by our biology, technology, and understanding of the cosmos. Spacecraft may eventually accelerate to a fraction of light speed. Cryogenic sleep may extend human lifespans temporarily. Propulsion systems may advance. But until then, the stars remain untouchable. This confronts a humbling truth. The stars are always visible, but not always reachable. We see their light, we study their spectra, we imagine worlds around them. But they exist in a realm that is fundamentally inaccessible for humans today. And yet, there is a paradox. Knowing the limits does not diminish wonder, it amplifies it. The stars remind us of scale, of fragility, and of opportunity. They are a canvas for imagination, a mirror reflecting human ambition, and a challenge that calls for patience, preparation, and humility. Humanity may one day cross these interstellar distances, but not yet. For now, our reach ends at the outer edges of the solar system, where survival is still possible. Beyond that, the universe is a realm of light, distance, and knowledge, but not yet of human presence. To look at Proxima Centauri and see a destination is to misunderstand both the universe and ourselves. The true horizon is not measured in kilometers or light years. It is measured in what humans can endure, survive, and sustain over time. The stars are there. They shine. They beckon. But for now, they are beyond reach. And in that tension between ambition and limitation lies the essence of human exploration, a desire to go farther, tempered by the reality of what we can actually achieve. Every civilization has looked upward and asked the same question: what lies beyond? For millennia, the night sky was a tapestry of mystery, a canvas for imagination, a compass for navigation, and a source of wonder. Today, humanity still asks the same question, but with sharper tools, sharper knowledge, and a sharper awareness of both the opportunities and the limits imposed by the universe. This examines the future of human space travel. What is possible, what remains theoretical, and how human ambition might eventually bridge the enormous distances that separate us from other worlds, even other stars. But as with every previous section, it is vital to remember that technology is only part of the story. Biology, psychology, society, and philosophy are equally critical in shaping what humans can truly achieve. In the coming decades, the focus of human space travel will remain on the Moon and Mars. The Moon represents humanity's nearest foothold beyond Earth, a testing ground for life support, sustainable habitats, and extraterrestrial resource use. Lunar missions are being planned not only by NASA and ESA, but also by private companies, marking a shift in exploration from government-led to multi-stakeholder endeavors. The Moon will serve as more than a research base. It could provide critical resources such as water ice, which can be split into hydrogen and oxygen for rocket fuel or life support. Lunar regolith could be used for construction, shielding habitats from radiation, or creating landing pads. The Moon is harsh, barren, and unforgiving, but it is also the bridge from which humanity can step further into the solar system. Mars, however, represents the true test. A Martian colony requires closed-loop life support systems, protection from radiation, food and water production, and technologies to manage dust storms, temperature extremes, and long communication delays. A human mission to Mars is not just a technical challenge, it is a logistical and psychological one. For months or years, astronauts will live in isolation, under extreme stress, with limited opportunities for resupply or assistance. Even with the best spacecraft, the journey itself will be a crucible. Bone density and muscle mass will deteriorate in microgravity, requiring advanced exercise regimens and potential pharmaceutical support. Radiation exposure will accumulate, raising cancer risks and affecting other physiological systems. and perhaps most profoundly, the psychological burden of distance, confinement, and autonomy will demand resilience, emotional intelligence, and careful selection of crews. Success on Mars will be measured not by speed alone, but by sustainability, the ability to maintain human life, productivity, and well-being in an alien environment over extended periods. This is a microcosm of all human exploration. Distance alone is meaningless if survival cannot be sustained. Reaching the outer solar system or venturing toward the nearest stars demands innovations in propulsion that have not yet been realized. Chemical rockets are effective for Earth orbit and lunar orbits, but they are prohibitively slow and inefficient for interplanetary and interstellar travel. Nuclear thermal propulsion has been studied extensively. By heating propellant with a nuclear reactor, it offers higher efficiency and greater thrust than chemical rockets. Nuclear electric propulsion, which converts nuclear energy into electricity to power ion drives, is even more efficient, capable of long-duration, low-thrust acceleration. Both approaches could shorten transit times to Mars or the outer planets, but neither can approach relativistic speeds needed for interstellar travel. Fusion propulsion offers a tantalizing prospect. By harnessing the energy of nuclear fusion, it is theoretically possible to accelerate spacecraft to a significant fraction of light speed. But controlled, sustained fusion remains elusive. Every engineering challenge, ignition, containment, fuel acquisition, is immense, and scaling fusion to power a spacecraft adds additional layers of complexity. Laser-propelled sails and other exotic concepts promise breakthroughs. Tiny spacecraft could, in principle, accelerate to tens of % of light speed under the push of powerful Earth-based lasers. But scaling this to carry humans introduces extreme engineering, shielding, and life support challenges. Moreover, deceleration at the destination is non-trivial. Without it, a spacecraft could pass a target star system at relativistic velocity, unable to slow down. In all cases, the challenge is energy density. Accelerating matter to relativistic speeds requires energy comparable to the entire global output for extended periods. Our current infrastructure cannot sustain it. Any near-term interstellar mission will therefore require radical breakthroughs in physics, energy generation, or propulsion technology. Even if propulsion issues are solved, humans cannot survive without the basics: air, water, food, and shelter. For missions lasting years or decades, resupply from Earth is impractical. Closed-loop life support systems become essential. These systems must recycle oxygen, water, and waste with near-perfect efficiency. Any leak or contamination can have catastrophic consequences. Food production in space remains a major challenge. Hydroponics, aquaponics, and synthetic biology may allow sustainable food production in small spacecraft or colonies. Nutrient delivery, energy efficiency, and psychological satisfaction from consuming real food, not synthetic pellets, are all critical factors. Humans are not machines. Nutrition affects not only survival, but cognition, morale, and resilience. Habitat construction is equally important. Radiation shielding can be achieved with regolith, water walls, or magnetic fields. Temperature control and structural integrity are non-negotiable. In microgravity, architecture must compensate for the lack of weight while ensuring safety during potential impacts from micrometeoroids or debris. Every element of the habitat is a life or death system. These systems must function autonomously for extended periods. Maintenance crews cannot rely on Earth for instructions when delays stretch into minutes, hours, or years. Redundancy, adaptability, and repair protocols must be designed for environments where failure is fatal. Survival is not guaranteed by technology alone. It requires integration of human skill, judgment, and endurance. As explored in Section 7, humans are the limiting factor. Section 10 builds on this by projecting into the future. Multi-year missions to Mars or beyond are not just engineering challenges, they are psychological and social experiments. Crew cohesion, emotional resilience, and the capacity for autonomous decision-making will determine success as much as rockets or shielding. Artificial intelligence may assist. Autonomous systems can monitor health, manage life support, optimize energy usage, and even provide companionship. AI may help maintain morale, manage schedules, and mitigate conflicts. But AI is a tool, not a replacement for human resilience. The human mind must still adapt to isolation, monotony, and the vast, indifferent void beyond Earth. Generation ships, in which multiple human generations live entirely in transit, raise profound social and ethical questions. How is culture preserved? How are decisions made when the original mission planners are long dead? How is population control, education, and governance managed in complete isolation from Earth? These are questions that no rocket can answer. They are questions of civilization itself. The future of human space travel is not purely technical, it is also philosophical. Every mission beyond Earth forces humanity to confront profound questions. What does it mean to leave Earth permanently? How do we value life in environments where survival is extraordinary, not guaranteed? What responsibilities do we have to future generations born in space or on other worlds? Can we maintain human culture, ethics, and identity in isolation for decades or centuries? Ethics of interstellar colonization also arise. Proxima Centauri b or other exoplanets may harbor life, even microbial. How do humans approach worlds that are not empty? The very act of colonization could be destructive. Space exploration is therefore not just a technical enterprise, it is a moral one. Every step forward must balance ambition, curiosity, and caution. Given the immense challenges, it is likely that robots will lead the vanguard of human exploration. AI-driven spacecraft, capable of decades-long missions, can scout worlds, analyze conditions, and even build infrastructure autonomously. By the time humans arrive, many logistical problems could be solved remotely. Hybrid approaches, robots and humans working together, may define the future. Robots can construct habitats, mine resources, and gather intelligence. Humans can perform tasks requiring creativity, judgment, and adaptability. This division of labor maximizes survival while extending reach. Robotics also minimizes risk. A robotic mission may fail or be destroyed, but no human life is lost. It is a way of testing the universe's limits without exposing ourselves to irreversible consequences. Section 10 concludes with a reflection. The universe is vast, indifferent, and unforgiving. The distances separating stars are measured in trillions of kilometers. Even the nearest stars are thousands of times farther than the Moon. Interstellar travel stretches human endurance, technology, and civilization to the absolute limit. Yet humans persist. We dream, we calculate, we plan. We build instruments capable of observing exoplanets, analyzing atmospheres, and even detecting signs of life across light years. Our minds can imagine journeys that our bodies cannot yet endure. Our civilization is learning to bridge the gap between ambition and survival, one technological, logistical, and philosophical step at a time. The future of human travel will be measured not only by distance, but by our ability to sustain life, culture, and civilization beyond Earth. Propulsion, shielding, and energy are important, but equally important are biology, psychology, and society. A spacecraft without resilient humans is a machine without purpose. A mission without preparation is a dream without foundation. Section 10 ends where all human space exploration begins, with vision tempered by reality. The Moon, Mars, the outer planets, the Kuiper Belt, the stars, each is a milestone, a challenge, and a horizon. Each teaches that the universe does not yield to desire alone. Survival, adaptation, and ingenuity are the currencies that allow humanity to extend its reach. We will travel farther. We will learn more. We will encounter challenges that test every limit of our bodies, minds, and societies. The future is uncertain, but it is also full of possibility. Because in the end, exploration is not merely about distance. It is about humanity's capacity to endure, to adapt, and to dream in the face of a universe that is vast, indifferent, and endlessly fascinating. And though we cannot yet touch the stars, we can continue to reach, to plan, and to prepare. The journey itself, the questions asked, the technologies developed, the endurance tested, is the first step toward the infinite horizon. Humanity's story among the stars has only just begun. And when the day comes that we leave our solar system behind, we will not be surprised by the distance, the isolation, or the challenges. We will be prepared because we learned to endure, to imagine, and to survive at every frontier the universe has shown us. The universe waits. It does not hurry, but neither does it forget. And humanity, though small, fragile, and ephemeral, continues to reach outward because it is in our nature to do so.